Okay, let's unpack this. We talk constantly about the autonomous driving, race level 2, level 3, level 5, and, the conversation almost always centers on these perfect, predictable environments.
Right. The pristine highways in California or, a test track in Germany.
Exactly. But if you really want to understand the deep foundational difference between the two philosophies in this race, you have to find the hardest possible problem.
You have to find the environment that breaks all the rules.
The absolute, undisputed final boss of driving.
And our sources argue that this place isn't a high-tech city. It's pure, glorious, unpredictable chaos.
We're talking about Mumbai, India. And we really need to paint a picture here because understanding this environment is it's critical to everything we're about to discuss.
It really is. I mean, if you haven't seen it, just picture a four-lane rotary.
Except the lanes aren't really there. They're just a theoretical suggestion.
Totally theoretical. And the traffic signals, forget it. They're basically just decorations.
And the mix of traffic is where it gets truly wild. It's not just modern cars.
Oh, not at all. You have these 40-year-old trucks just lumbering through. You have motorized rickshaws buzzing everywhere like insects.
Thousands of them.
Yeah.
And motorbikes weaving through gaps that, you wouldn't think a person could get through.
And the pedestrians just walk out into it. The road is just an extension of the sidewalk.
And then you get to the really unpredictable stuff, the true long-tail events that happen every single minute there.
You mean like the stray cows just deciding to sit down in the middle of traffic?
Yes. Or oxen, or even, and the source material is very specific about this, literal donkey carts.
Yeah.
Slow-moving, non-standard things that no computer was ever programmed to expect.
It's the ultimate stress test. And when you show that environment to the experts, especially from legacy automakers, their reaction is pretty uniform.
They all say the same thing.
They say level 5 autonomy there is absolutely impossible, period. The system just can't handle it. The chaos breaks every rule they've programmed.
So this is the core question for our deep dive today. If basically every expert using traditional methods says it's impossible, why is there one company, Tesla, that is completely confident it can be done, and maybe even soon?
What's the secret? What is that fundamental technical difference?
It's a huge philosophical divide. And our mission today is to synthesize the sources that argue this divide has created a tech gap of, 5 to 10 years?
At least. And we're going to get into the why.
Yeah.
It starts not with the technology, but by looking at the one thing that can successfully drive in Mumbai.
The human driver.
Exactly.
So let's start there. Back on that Mumbai street, you're watching a driver navigate this absolute storm of movement. He doesn't have a $50,000 LiDAR on his roof. He's not using some pre-programmed map. How is he doing it?
This is the first principle. It's what the sources say Tesla really focused on. If you just break down what a human is doing, the input system is actually, it's incredibly simple.
Deceptively simple.
Yeah. A human driver has two primary inputs. Just two eyes. That's it. Vision.
And that visual information goes to the processor.
The most powerful processor on the planet, the brain. It's this incredible neural network that takes in that visual stream and it makes judgments.
Split-second predictions based on a lifetime of experience.
Right. It's guessing the intent of that motorbike rider, judging the speed of that truck.
Yeah.
And then the output is simple, too. Hands and feet. Steering, accelerating, braking.
Eyes for input, brain for processing, hands and feet for output. That's it. It's all vision-based.
There's no radar, no ultrasonic sensors. It's a pure judgment-based system running on visual data. And that, right there, was the philosophical fork in the road.
So the idea became, teach the machine exactly like a human.
That's the whole foundation of the FSD project. Instead of adding more and more hardware to try and, brute force a solution, they decided to build an AI powerful enough to replicate what the human brain does with vision.
Okay, so let's get technical. How do you translate that human blueprint, that biological system, into silicon?
Well, you start by replicating the eyes. The system uses a suite of 8 cameras, not just looking forward, but giving it a full 360-degree view of the world.
So it sees everywhere at once.
Constantly. And all that raw video, all those pixels, get fed directly into one place. The FSD computer, that's the brain.
And this is where we get to that critical concept we hear so much about, end-to-end learning. What does that actually mean in this context?
What's fascinating here is that it's about not breaking the problem into little pieces. End-to-end means the entire process, from the raw pixels coming in from the camera.
So a frame of video showing, a green light and a cow.
Exactly. From that raw input all the way to the final physical action, the exact amount of torque to apply to the steering wheel, the precise pressure on the accelerator. It's all handled by one single massive holistic neural network.
One network for everything. Why is that better than, say, having one program identify objects, another one predict their path, and a third one plan the route?
Because you avoid what's called the handoff problem. In traditional systems, if your first module makes a tiny mistake identifying an object, that error gets magnified by the next module and the next, and it cascades into a huge failure.
Ah, so errors compound.
Catastrophically.
Mhm.
The end-to-end approach skips that. The AI isn't following a checklist. It's not saying, if I see object X, then execute rule Y.
It's learning the skill itself.
Precisely. It learns a direct correlation. It learns that this visual chaos requires this specific smooth output. It's learning to drive the way a person does through experience, not by following a massive pre-written instruction manual.
That feels like a monumental difference in approach. So if that vision-based method is so elegant, why did all the big legacy automakers go in the complete opposite direction?
Well, it really came down to caution and the limitations of the technology when they started these projects years ago.
Computer vision just wasn't that good back then.
It wasn't. It couldn't handle heavy rain or fog or bright sun flaring into the camera. And for a big car company, with liability and safety regulations, they just didn't trust that vision alone could ever be reliable enough.
So if you don't trust your main sensor, you add backups.
You bolt on everything you can think of. You add expensive LiDAR, which creates these super precise 3D maps of the world. You add radar, which is great at seeing through fog and measuring speed. You add ultrasonic sensors for parking.
And this whole approach is called sensor fusion.
Right.
Okay, but I have to say, on paper, sensor fusion sounds like the safer bet. I mean, more sensors, more data. Shouldn't that lead to a better, safer decision? The sources argue the opposite, which is counterintuitive.
It is, but this is the critical flaw. The problem is that these different sensors often disagree about what they're seeing. They all have different strengths and weaknesses.
So they're all shouting different information at the car's brain at the same time.
Exactly. And the car software has to try and figure out who to listen to. That's where the failures start.
Can you give us a concrete example of that conflict?
Sure, the classic one is a highway overpass. The camera system, the vision, it sees the road ahead is clear. It sees a bridge, but it knows it's an overpass. It sees go.
Okay.
But the radar sensor, which just sees things in terms of radio waves, might see that large metallic object up ahead as a giant static wall. It screams, "Stop, obstacle."
Okay, so this is where it gets really interesting. The safety hardware is now creating the danger. The system has conflicting inputs. It has to choose one. And to be safe, it has to choose the most cautious one, right?
It has to. It defaults to stop. And that's the root cause of phantom braking.
The car slamming on the brakes for no reason.
For no visible reason.
Yeah.
The car has a reason. Its radar told it there was a wall. The system spends precious time trying to decide who's right, the camera or the radar. And in that moment of confusion, it just hits the brakes.
How instead of a single confident brain making one judgment, the legacy car is having this frantic internal argument in real time.
A very dangerous argument. And that arbitration process, the code written to manage the sensor fusion, it introduces lag, it introduces error, and it makes the car hesitant and unpredictable. A human driver, or an AI trained on vision, learns to ignore that overpass. The sensor fusion system can't.
So that internal conflict is failure point one. But there's a second, maybe even bigger failure point. The outside world itself.
If we connect this to the bigger picture, even if all the sensors magically agree, the whole system collapses when it sees something it's never seen before.
This is the long tail problem.
This is the long tail problem, and the sources say this is the single biggest reason why the legacy approach is basically at a dead end.
So define that for us again, the long tail. Why is it so deadly for these systems?
The long tail's just all the rare, unexpected stuff, the things that happen once in a million miles. The high-frequency stuff is easy. Red lights, stop signs, a car braking in front of you, they master that.
But the long tail is the weird stuff, the bizarre things.
Exactly.
Yeah.
And the thing is, in a place like Mumbai, the weird stuff is the normal stuff. The long tail becomes the short tail. The chaos is constant.
So give us those examples from the source material. What happens when a legacy car, programmed in Germany, encounters something from the long tail, like a donkey cart?
Right. A donkey cart, something that was definitely not in the training data. The system looks at it and scans its database of known objects.
Car? No.
Oh.
Pedestrian? No. Bicycle?
And it comes up with nothing. It has a crisis. It has no pre-programmed rule for donkey cart. It literally concludes, I have no data for this.
So it just throws up its hands and says, I don't know what that is.
That is the perfect way to describe it. And because it's a rule-based system, it can't improvise, it can't generalize, it can't look at the donkey cart and infer, well, it's a slow-moving object, I should probably just go around it.
So what does it do?
It does the only thing its rules allow it to do when it's totally confused. It freezes, or it slams on the brakes. It just stops.
That seems like an impossible engineering challenge. You're trying to write a finite list of rules for an infinitely unpredictable world.
It's completely unsustainable. It means every time you want to drive in a new city, you have to spend millions of dollars and countless hours programming new rules for the local taxis, or the specific shape of their buses, or for their donkey carts. You can't scale it globally.
Which brings us back to the other approach. If the unexpected breaks the legacy systems, how does the vision-only AI handle it? And the answer is just scale.
It's a scale that's almost hard to comprehend. Your typical legacy automaker might have, what, a few hundred dedicated test vehicles, maybe 1,000, and they're incredibly expensive.
And they drive the same pre-map routes over and over.
Right, so their exposure to genuinely new long-tail events is tiny. Now contrast that with Tesla.
An entire fleet is the test fleet.
Exactly. Millions of cars all over the world are constantly collecting data. Every mile driven, even when the human is in control, the cameras are watching, the AI is running in shadow mode, learning from what the human does.
So it's a constant, massive, global data gathering operation.
Billions of miles of data, orders of magnitude more than anyone else. So when that donkey cart shows up in Mumbai, for the AI, it's not some terrifying unknown object.
It's just more data.
It's just another data point.
Okay.
It doesn't classify it as donkey cart rule set 42. It sees it as a slow-moving obstacle of a certain size and velocity requiring an avoidance path. Because it's seen a million other weird, slow-moving obstacles all over the world, it generalizes.
Okay, let's dig into that idea of generalization, this concept of adaptability and universality. This feels like the real magic trick. How can an AI trained mostly in, say, San Francisco adapt to the anarchy of Mumbai?
Because it's not just learning the rules of San Francisco, it's learning the fundamental physics and the social dynamics of driving.
So it's not learning to stop at a specific stop sign on a specific street, it's learning the concept of yielding to cross traffic.
Exactly. If the AI can learn to navigate a crazy intersection in New York City with taxis cutting it off, pedestrians jumping out, that skill, that core intelligence, is transferable to any other chaotic city on Earth.
Because the core challenge is the same, even if the vehicles look different.
The essence of driving is universal. It's using visual information to avoid hitting things and get to where you're going. That skill translates. The AI learns what a pedestrian turning their head means. It learns to read the intent of other drivers. And that's the same in Berlin or Bangalore.
So to launch in a new country, they don't have to start from scratch.
No, and that's the massive advantage. It's just a small adaptive training patch. You just show the AI a few thousand examples of local things like the shape of their traffic signs or how to react to a stray cow, and the huge existing neural net just absorbs it. It adapts.
It's not relearning how to drive, it's just learning a new local dialect.
The perfect analogy, and this all feeds into its internal model of the world, the vector space.
Right. This isn't a map, this is something else entirely.
A traditional HD map is static. It's a recording of what the world looked like 6 months ago. The vector space is the AI's live 360-degree predictive simulation of the world right now.
So it's not just seeing a car next to it.
No, it's seeing the car, representing it as a vector, and constantly predicting where that vector is going to be in the next 1, 2, 3 seconds. It's building this dynamic movie of everything around it, and then plotting the safest possible path through that predicted future.
So a legacy car drives on a map. The Tesla system creates its own map of reality in real time.
That's the dimensional leap. It replaces dependence on geography with dependence on intelligence. If there's a new construction zone that's not on the map, the legacy car is blind. The vision system just sees it and drives around it.
This really brings it all together. It's not just about LiDAR versus cameras. It's a complete clash of philosophies.
A total clash. On one side, you have the hardware-heavy, rule-based, geographically trapped systems. They're trying to build a perfect robot that follows perfect instructions.
An impossible task.
And on the other side, you have the software-first, vision-only, data-driven approach. They're not trying to build a robot. They're trying to build a simulated superdriver. An AI that learns the skill.
And that super driver ends up being better than the human we started with.
Way better. A human gets tired, gets distracted, has blind spots. The AI is never tired, it sees 360 degrees, and most importantly, its lifetime of experience is in 50 years. It's the aggregated experience of billions of miles driven by millions of humans.
So the sources conclude that the gap isn't just a lead anymore, it's something else.
It's a difference in dimension. The competition is still stuck, solving the problem of how do we make our sensors agree, while the other approach has moved on to solving the problem of how do we predict the intent of every object on the road.
To put it simply, the competitors' cars can only drive where they've been pre-mapped, 1 foot off that map, and the system fails.
Right. Whereas the vision system, because it drives by sight like a person, can theoretically drive anywhere a person can. A city street, a country lane, a chaotic rotary in Mumbai.
This is why they say the gap is 5 years, maybe 10 years, or maybe just in another dimension entirely.
They're solving a different and much harder problem.
So what does this all mean? If Mumbai really is the final boss, then the true start of the autonomous driving era, the real beginning of Level 5, will be marked by one single event.
The day a car successfully drives itself through that chaos.
That's the moment. When a machine can navigate an environment where lanes are optional and cows are obstacles, we'll know the problem of general intelligence for driving has been solved.
That success would validate the entire vision-only philosophy. It would prove that you can solve this with software and data, not just more hardware.
And here's a final provocative thought for you to take away from this. We spent this whole deep dive talking about cars, but the real breakthrough here isn't a car. It's arguably the world's most powerful visual AI.
Yeah. A general-purpose AI that can translate complex, chaotic visual data into precise, real-time physical action.
Exactly. So the really big question isn't just about driving. It's how this end-to-end AI model will be applied to other high-stakes problems. Think about robotic surgery, where an AI has to interpret visual feedback to make micro-movements, avoiding critical tissue instead of other cars.
The skill is the same, collision avoidance.
Collision avoidance. On the road, it learns to avoid a cyclist. In an operating room, it could learn to avoid a nerve. The potential for this kind of generalized intelligence, once you prove it can conquer Mumbai, is it's almost limitless.